Awesome. Come on in, sit down. Story time. It's wonderful. I'm very, very impressed with all the people that work for me that are here. This will reflect in your performance reviews. Don't worry about it. I normally have to pay you to listen to me talk, so this is wonderful. Hi, happy 3 p.m. on Friday, everybody. So I'm David, and if you've ever seen me talk before, normally all my talks are like about existential dread and like suffering and then finally succeeding. This one isn't, so don't worry. It's all good. It's Friday afternoon. I'm not going to bum you out. So what I want to talk to you about today is this weird kind of through line in technology that runs from a bunch of kids in MIT in the 80s through to John Carmack, all the way to like people doing the gritty in Fortnite in the 2020s, right? Or however you pronounce that, I don't know, I'm not 12. And basically how people's creative urge to make things with just about anything they have always basically succeeds. So there's a lot of code in this talk, uncharacteristically for me, and there'll be links at the end with samples, so don't worry about missing it. A lot of it's just representational. We'll get to building game engines from scratch in a web browser in a little while, but first we're going to do story time. And we're going to do story time about the first ever video game mod. Who's used a video game mod in their lives? Okay, about half the room. Excellent. Right, so in 1981, a couple of MIT students named Doug McRae and Kevin Curran started a company wonderfully called General Computer. I don't know if they believed in tenses. And they released their first game, a game called Super Missile Attack. Now, what was really interesting about Super Missile Attack is that it was an unofficial sequel to an arcade game called Missile Command, which you possibly heard of. And the two students had programmed that game by building an arcade modification, and it was a board that you physically attached to the original game. And they followed this up by making this game that they called Crazy Otto. Now, they used a similar technique, and they built a board that they soldered onto Pac-Man to make it work. And they basically accidentally invented game modding, right, for the first time. So what those mods did is they took the existing code and added some new features to the games to increase their difficulty, right? Because basically these were some of the first arcade games and people were getting too good at them and they wanted a challenge. So obviously, Super Megacorp's going to do what Super Megacorps do, and Atari tried to sue them out of existence. But instead, actually, they ended up hiring them. And as part of the settlement with Atari in court, they agreed never to sell unlicensed mods again, and Atari thought maybe they killed this whole weird modding thing dead. What that ended up meaning was that they had to sell Crazy Otto, this game mod that they made, to Midway, who owned Pac-Man at the time. Midway renamed it and released the game Mrs. Pac-Man. So it was the first game mod turned real thing. So I find this really fascinating because they were probably the first people to get into games in the way probably the majority of people that get into games today, which is basically through hacking the shit out of something that already existed and kind of butchering something using other people's game engines, right? So, in fact, this trend wasn't just restricted to general computer, and this trend of hacking arcade cabinets actually continued way into the 80s and into the 90s with often really unpredictable results. So unless you were born in about 1980 specifically, you've probably never played Super Street Fighter II Rainbow Edition, right? It was a hack so popular that Capcom cloned all of its changes to the rules of Super Street Fighter II and released it on the Mega Drive and SNES as Street Fighter II Championship Edition. Basically the fan favorite canonical edition of that game, and it all came from an unlicensed mod. Now, the weird thing about early gaming, and we're really talking about early games here, is it's really self-contained. So each game you made kind of required people to master a target platform, and the gameplay logic and the rendering code tended to all be kind of intertwined and the same thing. So you can see this at the time, right? Like early game ports, when you look at like an Atari and a Commodore 64 version of the game, they weren't really game ports in the traditional sense. It was more just someone squinting at one game and copying it and rebuilding it again for another target platform. So they were always complete re-implementations. So games specifically, they rarely shared code bases. Now, as games got bigger and more complicated, and bigger business and organizations, mostly motivated by getting to market quicker, started building games on top of their previously completed work. So this was most common in game series, obviously, So there are some funny anomalies, like Super Mario Brothers. The original NES Super Mario Brothers was built off the graphics code written for Excitebike the year earlier. Right? The momentum of the bike is Mario's running. And as the 1980s progressed, lots of companies started to build internal game development toolkits, they ended up calling them. And this was really just proto-shared code bases. Now, what happened then is this led through the 1980s and the early 90s into this boom in what was called game creation kits. So some people in this room probably are old enough to remember some of this. So some of them were private. So companies like LucasArts had the famous Scum tool, which they built originally for their point-and-click games like Monkey Island and a bunch of other adventures. So Scum, of course, was the script creation utility for Maniac Mansion, SCUMM. And other creation kits actually were launched as commercial products. So when I was a kid in the early 90s, I remember building games in Click and Play. I don't know if anyone remembers that. It was like a drag and drop-y thing. It was cool. But actually, Click and Play was an evolution of what someone called Gary Kitchens released as Gary Kitchens Game Maker. Very, very famous and probably the first. And actually, this idea of game creation kits continues today with tools like RPG Maker, which is still maintained and is 30 years old. Kind of wild, right? And there are still, like, I think Undertale was written in RPG Maker, so there's lots of like successful indie games still come from that. So while game engines didn't quite exist yet, everyone was clearly reaching for the same kind of thing. Like they were trying to share code, and like this is no different than the normal day-to-day work we do, right? Like that tension between sharing and just doing the work. So then obviously, I think all of my talks are about id Software secretly. That's actually all I ever talk about. So this all changed when id Software released Doom. Now, in 1993, Doom obviously popularized the user-created game mods. It was like a big killer feature for them. And they were spurned on by the fact that they kind of introduced network multiplayer, right? So then some commercial licensing of the Doom code base followed. Notably, Raven Software built Heretic on top of it, which was produced by John Romero from id Software, and the game Hexen, which was just Doom but with magic spells. And then Raven modified the Doom code base to extend its features. So there was this kind of, hey, we're going to license the game and some of the assets and kind of make it into a new game. Obviously, id watched this happen, and they were building Quake at the time. And they kind of realized that modifications were the lifeblood of the Doom community, and they were a reason it was so popular. So Quake introduced more than just a level editor, right? So it pioneered like a weird pseudo-C dialect called Quake C, which trivia is where I first learned C in 1996. And Quake C was built in as an extensibility point. So it was a fully compiled language based on C, specifically to extend game logic and the AI of the enemies. So id then started licensing the Quake engine to other games companies, specifically and most famously Valve Software, in 1998 to make Half-Life, which was then modified again, and it was called the Gold Source engine, the Gold Source. They just dropped the gold. And the funny trivia there, of course, is the reason it's called the Source engine is because they gave it them on a gold CD with a directory on it called Source. So then finally, Epic introduced Unreal and the Unreal Engine in 1999. So they basically had seen id's licensing model, and they realized that licensing the game engine was a whole damn business. And and the Unreal Engine is still popular today. It's probably the most popular engine in the world. So interestingly, while mostly lost to history now, Ken Silverman built the Build engine in 1995 to run Duke Nukem 3D and Rise of the Triad, I think, which came out the following year. Now, it's funny because it isn't really clear where the name game engine came from, where the terminology game engine came from, because it wasn't there for Quake. And Ken Silverman kind of called his thing the engine. So conventional wisdom seems to be that id adopted the name engine when they started licensing it, copying Ken Silverman's naming, and then Epic kind of copied that and started licensing a game engine, and that was the origin of the term. So yes, Valve only knew it as Gold Source before game engines. So much of that terminology that we have to talk about, all of these legacy engines, was retrofitted on them during an explosion of reusable game engines in the 90s, in the early 2000s. And the id engines, like the Quake engine, the Doom engine, if you're into this stuff, have been kind of retroactively renamed as idTech 1, idTech 2, through to 7, I think we're on now, which is the current modern Doom engine. While the Unreal engine still maintains its version history back to Unreal, which is kind of fun as an artifact of the time. Now, often this is the question that most people struggle with, like what actually is a game engine? And if you follow video game discourse on the internet, which I would greatly recommend you do not, lots and lots of people have lots of opinions on video game engines and people rewriting them, and they're mostly wrong because they see engines as these monolithic single systems. A game engine is really just the framework that provides a programming model for you to build a game inside of, right? Much like a web framework or anything else. So they tend to come with lots of optional libraries and modules and subsystems that are capable of diverse ranges of things. And they tend to have an opinionated model of how they think a game should be constructed. So they're largely like a structural design pattern for the games. They normally come with modules for things like rendering graphics, handling input and audio, invoking game logic code, AI systems, data streaming, networking, all these kind of subcomponents. So engines are often modular and can be customized and extended by developers who do the unique parts of their game and the custom game logic. And on top of all that, engines are often useful because as long as the engine's code base itself gets ported to different platforms, you kind of get built-in portability. So you tend to write your game once and mostly can target everything with only a little bit of difference here and there. And that's basically why whenever you read someone slagging off Bethesda for still using the same engine for Skyrim as they were using for Oblivion and Morrowind, you can realistically think of them as idiots because actually they're just saying the graphics look bad, or I don't like the funny way Funny Man walks. Like it's very cheap, calorie-free criticism. So for reasons I'm going to get to later, I ended up building a game engine that runs in web browsers over a period of about 10 days a couple of years ago because I'm an idiot. And so I want to dig into some of the subsystems that we had to build to make this engine work. So here's the obligatory caveat before we start. There are many valid designs for game engines. These are just some representative examples. This is not an exhaustive list of anything you could ever put in a game. I'm looking at you YouTube video readers in the future. Yes, I know I missed the thing. So consider this kind of an introduction to some of the concepts rather than an exhaustive lesson. Okay, so we're going to start off with the most core of concepts in most game engines, so the game loop. Not all games run on a game loop, but most real-time games where like the images update in real time tend to, and games tend to run at a fixed tick rate, so the game is evaluating its state in an infinite loop, and they poll for user input, they increment AI, and execute any user-defined game logic as the ticks step forward. Now traditionally, a game loop would tick at a fixed refresh rate, but over time, most game engines have decoupled the internal tick rate of the game engine from the rendering logic and the loop ahead of it. This is actually why if you ever try and play old like DOS games on modern processors, they run too fast because your computers are running too fast now. Now renderers or rendering engines tend to take a bag of game state and they generate visuals for the game. So 2D renderers are really generally concerned with rendering order, so sprite animations, camera positioning and post-processing effects if they need to. And 3D renderers, on the other hand, tend to deal with things like 3D asset loading, texture mapping, applying various post-processing effects, and invoking GPU calls. So renderers generally target specific graphics architectures, so they will target different low-level APIs like DirectX or Vulkan or Apple's Metal to support different target platforms. So generally all that work goes into the engine rather than the game itself. And then finally, we often have this concept of scenes in games. And I guess, you know, if you're building a server-side web app, you're probably building MVC, you have controllers, right? Well, a scene is normally the unit of abstraction that games are organized into. Now, not every game engine operates on this concept of scenes, but I know, you know, Unity does, I know Unreal does. And a game may have like a main menu scene or an options scene, a real-time gameplay scene, perhaps maybe mini-games are organized into different scenes. You can kind of see them as abstractions over the types of interaction modes. They also tend to contain groups of resources that are relevant to that kind of gameplay. So to bring some of these concepts to life, I want to take a look at an admittedly very, 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 very over-designed implementation of Conway's Game of Life, which, to under-design it, you can probably write in about 10 lines of code. So if you haven't heard of it, the Game of Life here, also simply known as Life, is a cellular automation game devised by John Horton Conway in 1970. Now the idea is it's designed as a zero-player game, where the game's initial state, governed by its rules and some randomness, will play itself out requiring no user input. That's the idea. So the Game of Life takes place on a 2D grid, like a graph paper, and you can play it by hand, where each grid location can either be alive or dead. And after each game tick, the game runs some logic and updates its state to change the images. So the rules for the Game of Life are this: any cell with fewer than 2 living neighbors dies because it's underpopulated. Any cell with 2 or 3 living neighbors lives on to the next generation, so it survives. And any cell with more than 3 neighbors dies because of overpopulation. So you've got all these little flickering cells. And then finally, any dead cell with exactly 3 living neighbors becomes alive as if it's been reproduced. So it's a rudimentary simulation of life. And that's what it looks like. So we're going to build a game engine that can run this game. So that looks just about big enough. It's TypeScript. Sorry, everyone that can only see C#, but it's basically the same in any programming language. So first, all we're going to do is we're going to define the most minimal possible engine and a few interfaces, right? So our game engine has an instance of an iRenderer and an iScene. I tried to write it .NET-y. So the scene can be set up from the calling code, and we've implemented our game loop there. So what all the game loop does calls update and render on our scene as we attempt to step the world forwards 100 milliseconds at a time. And we're using the browser's request animation frame because we're going to paint this with Canvas because it's easy. Now, we need a little bit of startup code here, so we just created a HTML file with a canvas for our UI, and the startup code that glues these 2 bits together. It picks up the canvas, creates an instance of our canvas renderer and our game engine, and we set all the stuff up. Now, our Game of Life scene implements this iScene interface, and in it, there's an init function, an update function, and a render function, along with an iterator that lets us loop over each of our cells sequentially. So you can see how we're building up the rules of the Game of Life inside the scene here. And if we zoom in on our update function, those are the rules. That's the things expressed in code. Now don't worry about reading all of the implementation in detail, really. But what we're really doing is we're just looping, we're taking a snapshot of the game state, and then we're looping through everything, applying those rules to produce a new game state before finally updating the world state ready to be rendered. So the logic is all in the update function of the game. Then finally, in our render call, we loop through each of our cells again, and we're just going to draw a black square or a teal. Teal's a nice color, depending on whether the current cell is alive or dead. So our renderer is really dumb right now, there's no graphics code to speak of in here, but it can draw fabulous rectangles. That's my renderer. And this is our basic canvas renderer. So it wraps the browser's native APIs, it draws 2D squares. One of the things you might notice, and one of the annoying things about doing stuff like this in the browser, is that we're inverting the y-axis here, because most games you think bottom left, browsers think 0, 0 is top left, so we've got to flip some numbers. And it works. And that's it, that's the whole of the Game of Life. And it's cute, and actually if you can disappear down a Wikipedia black hole around how you can produce specific game states that get locked into infinite patterns and all sorts of stuff. So obviously, like I said, this is a very, very over-designed version of Game of Life. You don't need all this for this. But it's a good example of some of the principles behind game engines. Now, while watching the Game of Life play out in all of its zero-player glory over and over is really fun, it's the most fun I can imagine ever having, most people kind of want a little bit more from their gameplay. So let's talk about input handling and wiring all that stuff up. So generally, input handling subsystems are used to convert input from things like gamepads and mice and keyboards through what most game engines call a key map. And that key map translates your input into game actions. It's the reason you can use multiple gamepad types and keyboard controls and mice and joysticks and things. And then those game actions are passed around the game rather than plumbing in the direct controls. So having this level of abstraction is just useful, especially if you're doing cross-platform. So obviously also all the esports players love that because they can produce better keyboard layouts than you can. Now, we're going to need a game to rip off for our next example, and there's this excellent little platform game that started life as a Flash game in 2010 called Thomas Was Alone. It's a game about a computer mainframe gone wild and a malfunctioning AI, and you should play it. It's actually really funny. But most importantly, lots of its characters are just square objects, and you can see them in the video here. So given I have a renderer that's really good at drawing squares, we're going to make the best game I can ever imagine. David Was Alone. And we're going to start with the input handling. So we're going to build on our previous example, right, on our glorious Conway's Life engine. And we're going to add a new interface, the iInput device, to our engine. Now, the input device implementations are going to be responsible for mapping input to the object containing the currently requested game actions. Thankfully, the modern web browser is actually really good. I know that's a controversial statement sometimes. And it already has built-in support for Bluetooth controllers and keyboards and joysticks and basically any peripheral you can plug in. And touch, of course. So here what we're doing is we're updating the game engine to keep track of the connected input devices just in an array. And we're going to modify our game loop to pass this collection of input devices to our scene on each update, and the scene then can just check the input devices. Finally, we're going to expose a function for our startup code to wire all this stuff up, right? So this is a keyboard class. It's super, super boring. All we're doing is we're wrapping the browser's keyboard events from the event listener APIs and just keeping track of which keys are pressed in a set. So when current actions gets called, when get current actions gets called, we return an actions object with the state set for left, right, up, down. So those are our game actions because we're thinking in 2D. And you can see here that using the gamepad API isn't much more complicated. This allows us to use kind of a D-pad on a standard Xbox controller or a PlayStation plugged in via USB. So we're keeping track of which gamepad is connected and querying its button state to get current actions down on line 26 there. And then finally, this is now our level scene. Now, in our level scene, we flatten all these controller inputs down and move our hard-coded player character object when a valid game action is requested. So we're just changing the coordinates that we store in the state. Now, luckily, because David Was Alone is made up entirely of squares, our existing renderer is perfectly fine for this. So in the top corner, you can see where we've changed the input on the index page to add our keyboard controller by calling connect input devices. So just a little bit of startup glue that goes up there. And then, basically the same thing in the same structure. So David might be able to move, which is wonderful. He's also defying gravity and is still very, very, very alone. So all we're doing here is just moving where a square gets rendered on the canvas by updating some coordinates. It's not truly a character with any behavior because we're not modeling any kind of game entities yet. Now, at the moment, we don't really have a player character. We just have a square. Game engines generally keep track of entities like any other system where you collect data, right? You build things like this every day. And obviously, just like any other program, an entity tends to be a collection of data, sometimes stored alongside its behavior, and it's a little bit different in games than in other systems. Now, building game entities for behavior helps us keep all of our logic out of the main scene, right? And in simple games, it's fine. You could build Snake or Conway's Game of Life by just hoying all your code in the update function and getting away with it. But anything where you're building systems that have to interact with each other, it just doesn't really work very well. So think of them as an organizational pattern. And to add that concept of entities to our code base, first, we have to create a new draw function, right, on our iRenderer interface to keep all of the display logic abstracted from the game. Now, we're going to add a couple of new interfaces, an iUpdatable that describes anything in the game world that can be updated as the game ticks forwards, and then a game entity that has a physical location in the game world, an X and a Y coordinate, and a width and a height, which itself is updatable. So we're taking all these characteristics that have been littered through the code base and we're giving them form. Now, this lets us move all of that logic for updating our player scene into our new player character entity and generalizes our level scene, which is now just responsible for collecting all of the entities that exist in the scene and ticking and calling update on each of those things. So it might feel like we're just kind of cutting and pasting code around, but what it does mean is we can now add other kinds of entities that share those same characteristics that are drawable and movable. Now, another approach that people often use to solve this same problem is something called entity component systems. Now, this is a very game devy pattern, and the language is a little bit tricky here, so I'm going to talk about the terminology a little bit. So in traditional object-oriented design, data is co-located with functions that apply to it. So that is the classical OO language kind of a description of this thing. Now, games in the late 1990s, notably if anyone ever played Thief the Dark Project, they pioneered the idea of entity component systems, which are kind of the opposite of OO, because what they say is, hey, having lots of objects in memory is really performance intensive. And actually, most of our games are bags of data. So they separated the state that was normally in objects from the logic that applied over to that state. If anyone was in Layla's talk yesterday, she spoke about the idea of a blackboard, and that it's basically that same concept. Now, the thing that glues this stuff all together is like a registry system, hence entity component. And so there's a registration table that maps the data elements to the various behaviors that mutate the data. Now, at that point, all you have to do is you tick the subsystems rather than ticking the entities, which is a kind of an inverse design pattern here. So what this does is it changes our relationship to the way we do performance optimization and data organization in our program. So inspired by this, and though not explicitly in ECS, in the 2D engines that I've built, I like the idea of introducing this concept of characteristics, right? So characteristics are attributes that entities can maintain a subscription to, which can then be used across multiple entities in the game world. So for example, both the player and the enemies can be physics objects, right? So they have weight and gravity applies to them. Players and maybe multiplayer characters can be movable objects. Enemies can be movable objects. I like using the word characteristics or behaviors because it avoids the use of the very, 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 very overloaded word component. Because component is the word that we probably need to take out of all of our programs today. So to adapt our engine, we've added an update context here that contains our game state to be passed around to on each update of the game loop. And we've modified our game entity to contain an array of characteristics, and we've made being updatable optional on the entities. And then, of course, we just added a very simple interface for characteristics to implement. Now, our level scene is now responsible for triggering the update function on any characteristic that our entities have applied to them, and then optionally calling update if there happens to be some actual logic in the entity itself. Because what you find is as you build up these set of characteristics, most of the logic gets pulled out of the entities. So our entity class is now slimmed down really to a minimum here, while allowing us to share our characteristics between entities. And one of the nice things about generalizing these behaviors is you just can use one system to apply to different things. So I guess I would describe ECS as a form of composition rather than inheritance, if you're looking for kind of parables for what you see in your normal programs. You'll notice in this example, I'm just adding an instance of the characteristic to an array. In a real ECS system, there's normally a registration table that you interact with, but it wouldn't fit on the slides easily. Now, while moving our existing behavior into an ECS-like structure might make our code look a little easier to reason about, it's also prepared us for adding the physics system to the engine. This is because having physics apply to something can be implemented in the same way. So physics simulations are really interesting in video games. They vary wildly based on the kind of games you play, mostly because real-life physics sucks. Like, if you fall off a cliff, you just die. And most people do not want that experience in video games. So for our 2D side-scrolling, we're basically doing Mario physics, because Nintendo are really great at finding this game feel where the physics is the fun bit, where it's not punishing. Now, to do Mario physics and have that kind of floaty, wonderful arc of a jump that you can control, we need to rework how we implement our controls. So rather than just forcibly moving people left and right, what we're going to do is we're going to add some variables to store like an object x and y velocity so that we can have people glide and slow down and accelerate and decelerate. Now, we've set these values in our player character class, and we're also adding this new physics object characteristic after the controllable characteristic. So the controllableness and the physics object can both interact in sequence. So next, we're going to update our controllable characteristic to increment or decrement this idea of velocity when keyboard buttons are pressed, along with implementing a maximum cap. So what that means is when you press and hold the key, you will get like a gradual acceleration up to a speed, and then it will ramp down. We also obviously are going to add support for jumping by having a velocity Y volume. And now finally, we can implement our physics object characteristic itself. Now, I'm not going to reproduce the entire code of the characteristic here, but I want to call out a few important things. So firstly, we're calculating some collision points, so a line on the bottom of the box around the character. Now, this is important because it gives your collision detection both a solid way to find the ground. You have to know, you can't jump if you're in the air, you have to stop people from falling, but also it's a little bit of give when colliding during jumps, right? We want to make sure that we're only checking certain points. We're also applying gravity. Now, we're going to implement jumping just by splitting the amount of time it should take for our object to fall by 60 frames a second. Now, you can obviously, what you should probably do is get the current frame rate based on the refresh rate of the screen and split it down, but let's just go with it on this example. So combined with the modifications to controls that set the velocity, that means that when someone presses the jump key, the entity will first move upwards, slowing down as gravity applies, end up with a negative velocity until it hits the ground. Right, so you get this beautiful little arc. Now, actually implementing falling is done when we calculate gravity, so a speed that the entity will fall, like in basically pixels per tick. If they're ever not on solid ground, we just make them fall, always. And we increase the speed until they reach a terminal velocity, otherwise your game gets very, very weird when you drop off a big cliff and you start to plummet down towards the ground. So after adjusting these X and Y velocities, we apply movement to the entity, shifting it to the next location on the screen. No, we're not going to change. There we go. And that's what it looks like. So that is the kind of the nice Mario floating arc of the thing. David can fall, he can jump, but he's still alone. So, hi. I first did this talk in a foreign country. In the UK, there's a kids show called Blue Peter, is what it says in my notes, but I think you're probably mostly familiar with the idea of Blue Peter. So it's the longest running kids TV show in the world, I learned while researching for this talk. So they frequently show you how they build things out of paper cups and string, and then they bring out a Ferrari and say, oh, don't worry, we did all the rest off screen. So if you'll allow me a bit of a Blue Peter moment, we're going to jump from David was alone to here's one I made earlier. So a couple of years ago, during doing preparation for a conference booth, I spent 10 days building a game engine that could run in a web browser, right? The idea was that attendees could walk by and play the game, competing asynchronously with everybody else that walked by that day. And the cool thing that we ripped off was like a Mario Kart-style ghost feature, where it was a platform game where you got to race to the end, but you could all play against the ghosts of previous players on your local device. And we had a big screen where you could see everyone playing in real time, running around the level. It was super, super cool. So as we move to talk about graphics, I'd like to introduce you to the magnum opus that is called I Am Jam, the game where you, a humble orange, try to become jam. It's great. So this was all Joe's artwork, by the way. I didn't draw this. So here's one we made earlier. While I was working together on the nuts and bolts, Joe put the pixel art together for all this stuff, and it's beautiful. So other than how good they all look, there's nothing really special about the graphics here. Like, this is just a couple of JPEGs for the background art. It's some keyframes for the mice. Those are just frames in GIFs, basically. And we need to get these into our game engine so we can draw more than just squares. So if you've ever seen 2D games before, you'll have probably heard the word sprites. So all a sprite really is an animation sheet made up of several images that get played like a flip book, right? And much like our earlier player character entity in the code base for I Am Jam, we had to design an entity that keeps tracks of the animation frames so that we can increment through each frame as the game ticks forward. Now, obviously, if you flick the animation every frame, you're not going to see anything. It'll just be a flickery mess. So you've kind of got to shift it every couple of frames to get that nice, smooth, pixel arty animation. So our game used two conventions. We both supported animated GIFs, which we could write to the HTML canvas directly. And we also supported a sequence of images in a sprite sheet that we would move along between. So 2D engines generally use flat files for all this stuff. The flat files are called sprite sheets, and if you ever like decompile an old game or a ROM, you'll often find like a big blob of bitmap data, which is just all of the graphics spliced together that the engine knows how to parse. And then basically there's some code that does byte offsets to pick the right thing. That's how every Mega Drive game and every SNES game worked. Now, this is the character class from I Am Jam. It's a touch busier than the one from David Was Alone, mostly because I wrote it earlier and it's a bit worse and more complicated. But we have two sprites associated with our character, one for them living and one for when they die. So we have this cool like orange rotting away peeling animation when they die, and you still want the sprite to update when the player goes away. So our character class initializes its sprite on loading, and each time the game updates, we call tick on the sprite. The sprite then evaluates if it needs to animate, if it needs to cycle the next image forwards. Now our drawing logic is a touch more complicated because the character state, like whether they are standing still or jumping, can influence which sprite frame we play, because when they jump, we kind of want to hold an animation. Once we work out if they're alive or dead, and if they're moving or not, we pick the correct sprite and we call the draw animation. So it's the same kind of structure. Now the sprite class is responsible for loading all the frames from our sprites in sequence, and also creating flipped versions for when you're running backwards. Otherwise you have like a weird moonwalking thing going on. There's some low-level image manipulation here done with the confusingly named but awesome libgif JavaScript library, bit of a mouthful. And every 5 game updates, the frame counter will proceed and the sprite cycles its frame. So this class is responsible for drawing the image directly to the canvas, as the render in I Am Jam is a little bit different than our previous example, so it has access to that canvas. And it works. You get these like really cute animations. I really should have looped that video. We're going to see that again. There we go. Our bounding mouse trying to catch you. Now, in 2D games, there's this idea of rendering layers on top of all of this. Now, from back to front, kind of like using Photoshop, if you ever use Photoshop, most people have, the background layer is the furthest layer from the camera. Generally, it contains static images and fixed assets, right? So a sky or some mountains. Then you end up with a middle ground layer. Now this normally adds elements that are closer to the player, so things like trees and buildings and other objects. And then finally a foreground layer, which typically contains the game's characters and enemies. So because our background is one big image in this example, we're just going to draw back to front, which is a little bit wasteful, but we have the computing horsepower in 2025 to do this. So we're using like a Z-index system, like CSS does, just to pick which gets orders first. And you can see from this kind of rendering analogy on the screen how we're looking through a transparent vase that we've got in the foreground, which is literally a transparent GIF that we're writing on top of the pixels. So you can kind of have the orange character pass between it. It's pretty fun. Now, for this game, we implemented this really super lo-fi camera that works out what to draw in our canvas based on the coordinates of the player in the game. So based on your position, it basically scrolls the background. The assets never move, just the background moves left and right as you use your controls. And then it has a little bit of bounding on the edges to make sure that the end doesn't scroll past the canvas nor the start scroll that way. And instead, once you get there, we switch to moving the character for that little bit. Now, traditional 2D games were often made up of tile sets and level data, where a tile set is a palette of reusable chunks that were used to conserve memory. Now, this is super, super common in any memory-constrained environment, right? And basically, it's the difference between having lots of copied data or using references to objects. So traditional games would have a tile set, and you would paint levels out of references to the different tile types. And generally, different tile types would be passable or solid or destructible and have different characteristics baked on top of them. And you would make levels out of all those things. And, it's really good when, you've only got 100 kilobytes of memory. Our background is only 130 kilobytes. I think we're going to be okay. So we don't really need to use tile sets in our game, but that is what you would have done back in the day. So finally, we've got our character moving, we've got backgrounds, we've got layers, we've got behaviors. We need to do collision detection finally. And now collision detection is different depending on the kind of games you're building and the kind of game engines. And in 2D games, generally we use something called bounding box collision detection, which is super, super common. So the idea is that each of our game entities has a box drawn around it, and the way that you do collision checks is you just check where those boxes intersect. So it's relatively inexpensive. So as the game ticks, the player character checks if it's colliding first with the environment or any other entities in the scene. Now, we make this cheaper by, instead of having to check all of the lines around the bounding box, you can identify some hotspots, top left, top right, middle bit in the middle. And you only have to do 4 or 5 checks rather than checking all the pixels around the edges of all of your entities. If you've ever used game engines like Unity, you might have heard those collision detection routines called box colliders, or AABB, which stands for Axis Aligned Bounding Boxes. That's the technique that is basically this, but in 3D games. So we're using this really, really fun little hack for level geometry collision detection in this game engine. All we do is we have a second image that matches exactly the dimensions of our level background, and we use the colors of the specific pixels to determine if the terrain is solid, or if it will kill you, or if it's the end of level goal. So it's a really, really simple hack, and the reason I chose this technique is most real game engines come with level editors, and you don't want to be screwing around with this data by hand, so we could just paint this. So this is really easy to do in a browser because you can use the API getImageData, so you can load an invisible copy of an image and say, give me the image data at this precise pixel. So all we need to do is we've got all of our little points on our entities, and we just say, hey, what location are you at in the world? Well, give me the color in the other image. If it's red, you're dead. If not, you can move. If you obviously had a drastically larger level, this approach would probably not scale because, of course, we kind of have these accurate pixel colors for everything, so the file would get very big. But, I truly think sometimes the best level editor is just the MS Paint you know. So our enemy collision mostly works on these hotspots, and this is a cool debug visualization that I wrote when we were building the game to try and work out why things were dying or why they weren't when I had mistakes. So I think this is the easiest way to see it in action, right? You'll notice that the red points on the entities are moving in the game world, and the points that have an overlap have collided. So that player died, and if I go back again, you'll see that green thing with 2 spots is a mouse, and the square is an orange. And the nice thing about this is that orange can clip through the back of the mouse without dying. So you don't get this really, really horrible, precise collision detection that makes games punishing to play. So we're really optimizing for game feel by manipulating the systems here. And a lot of 2D platform games do this. Like if you really pay close attention, like lots of famous games, like they have Coyote Time, where if you run off a cliff, actually you can still jump for a few pixels afterwards. And if you just clip the edge of an enemy, it just won't damage you as if by magic. So all of this is just to help you find the fun. So our code to deal with player death exists in the update function of our enemy entity, right? So every time the enemy ticks, it's basically saying, hey, have I killed something yet? And if it has, the characteristic inside it, which is killable, actually does the check. And killable just means something that has health in this game engine. Something that has health is killable, and the killable characteristic will remove the health. Okay, so this is really useful. Did anyone see Layla's talk yesterday, the day before? Brilliant. Oh, God, I wish it was more of you because it was brilliant, and I'm about to skim over the subject she spoke an hour for. So watch it on YouTube when it comes out. So AI in games is like a huge, vast topic that covers loads and loads of different approaches. It would literally be impossible to cover all the different techniques for AI in games in this session. So the way it's triggered, however, is generally consistent with all the other game loop things. So every nth tick, the AI for each of the entity, has a thought. It implements its logic. It executes something, and maybe it makes our player do something, or it makes an enemy do something. Now, most games have some kind of pathfinding AI. That's the most obvious AI that you will see when you watch enemies walk around. And that often uses something called a navigation mesh. So they're basically invisible roads that you paint in all the 3D levels, And when the characters are running around, they're like, oh, that's a road, I will walk on that road. So it's the reason that, if you're playing a game of GTA, the pedestrians walk on the sidewalks, because there are invisible tracks painted there that they run along. There are common algorithms for this kind of stuff, things like the A-star pathfinding algorithm and other related techniques. So games like Halo popularized something called behavioral trees, where characters have sets of actions they can pick from, whereas GOAP, goal-oriented action planning, is popular in games with emergent gameplay, where the game entities are given a goal and a set of actions they can choose, and then they resort and prioritize their actions until they get closer to that goal. That was probably first popularized by the game Fear, which was like 20 minutes of Layla's talk yesterday. It's really good. Please go watch it on YouTube. In the games of the late 90s, there were experiments in using neural networks, so games like Creatures, if you remember that, and Black and White. Finite state machines were used in games like Doom and Half-Life, where, again, different ways of modeling characters with actions. And actually, there are lots of interesting hybrid AI approaches. So famously, if you've ever played the game Left 4 Dead, there was an AI director, and it was there to antagonize you. The whole point of the AI in Left 4 Dead was every time you play cautiously, spawn more zombies. Every time you leave your group, spawn more zombies. So they used it to control the pacing of the game, which was pretty innovative in 2007, 2008 when that came out. So if you're interested in deep dives about this, either Layla's talk or there's a really good YouTube series by a guy called Tommy Thompson called AI in Games that does a lot of AI deep dives into topics. But for completeness, I just want us to take a quick look at the artificial intelligence, extremely artificial intelligence, in I Am Jam. It's that. So the AI in this game is really simple, right? It just runs from left to right and attempts not to fall off cliffs. Which, I mean, to be fair, me too. Our simple AI just gives an enemy an X velocity of 4 pixels per tick in whatever direction it's facing. Every tick, the enemy evaluates if it's about to fall, so it looks ahead and sees if there's a hole. This is just a collision detection check that just looks 4 pixels ahead of it. And when either of these conditions are met, it turns around. So it's a wonderfully disorienting mouse that just confuses itself. This means that our AI will run backwards and forwards along the platform it spawns on, but won't fall into the pits and kill itself, which was the first version of the game. All the mice fell from the ceiling, ran along the platform, and dived into pits, and it wasn't very hard. So the second version of the game, I wrote a really aggressive AI, and what it did is it would turn around whenever the player passed it and chase. Unfortunately, you die really quickly when there's loads of entities that, as soon as you cross the middle point, turn around and chase you. So it just wasn't fun, right? And I think one of the really interesting things about AI in games is most of AI and most of game feel is about finding that fun. So I thought it was a really good example of making my AI dumber just so the game was playable. So I can't do a whole talk about making a game without letting you try the game. I haven't checked this QR code today, so someone tell me if it works. Yeah, it should work on your phones. Also works with touch, works with mouse and keyboard. You can connect an Xbox gamepad to it because why not over-design everything? And I'm super proud of how this fun little game works, is the truth. And the event that it was used at, it was a hit. People loved it. We had people trying to exploit the game engine by playing on Macs with faster refresh rates than I had envisaged it running on. We had to patch that halfway through because there was a leaderboard. Very good. It was nice to watch people race. So as you see the game, there's also kind of a secret where if you go up when you jump, you'll do like a high jump. So there's a huge amount of game engines out there that will help you on your way to building games if you want to build games, is the truth. I do think that if you're looking to learn about the primitives that go into making a game engine, this is a really good way of understanding the constraints that you're signing up for when you pick a game engine, because like any framework, a game engine constrains the things that you can do. That said, in the 2020s, the reality is like the amount of target platforms and hardware out there, it's very, very unviable for most people to make game engines from scratch for anything more than very simple games. So, if you're going to build a game, go use Unity or Godot or Unreal Engine or something like that. But I still kind of think there's something beautiful and fun about doing it yourself just to see what it's like, you know? I hope you've had fun here with me today, and I hope you're at least a little bit inspired to use programming for something that isn't boring capitalism. Thank you for coming, everybody. I really appreciate it. I know it's late.